This is a male honeybee, or a drone. All drones have only one parent. That's because they are born from unfertilized eggs that are supplied by the queen, which is female. Female bees, on the other hand, are born from fertilized eggs by sperm collected from the drones. So females have two parents, a female and a male. The same goes for every generation. Each male has one parent, and each female has two. So one drone has one parent, two grandparents, three great-grandparents, five great-great-grandparents, eight great-great-greats, and so on. You might already recognize this sequence of numbers as the Fibonacci sequence. The Fibonacci sequence is defined by one simple rule. Every term in the sequence is the sum of the two previous terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and 5 plus 8 is 13. If we want the next number, we add 8 and 13, which is 21. In fact, we can phrase this a different way. To find the next Fibonacci number, add the current number to the previous one. These are what's called recursive definitions. They define each term by its preceding terms. They're helpful formulas if you happen to know what those preceding terms are. But let's say you want to know the 100th Fibonacci number. If you don't know the 98th and 99th numbers, then this formula is useless. You would have to find every number up to the 100th term, which would take an unreasonably long time. So let's see if we can find a non-recursive formula, one that doesn't depend on any other terms in the sequence. First, watch what happens when we take a Fibonacci number and divide it by the previous number. Starting with the first two terms, we get 1. You can see, as we do this with bigger and bigger numbers, the quotient seems to get closer and closer to some other number. The further we move along the sequence, the closer the quotient gets to whatever number that is. In fact, if we take the limit of this quotient as we approach infinity, it'll be infinitely accurate and therefore equal to the number. So how do we find it? First, we need to call it something for now, so let's call it x. There's another way we can express this value of x as a limit. We could also say the ratio of fn plus 1 over fn. This is still the same thing, one Fibonacci number divided by the previous one. From this recursive definition, fn plus 1 is equal to the sum of the two previous terms, so we can replace the numerator of this fraction. That allows us to split it into the sum of two fractions with the same denominator and take the limit of each one separately. For the first one, fn over fn, anything divided by itself is 1, and the limit of 1 is 1. For the other limit, notice how this fraction is the reciprocal of this one. And this one is equal to x, therefore, this one is equal to 1 over x. Now we have an equation which we can solve to find x. To do that, let's multiply every term in the equation by x. That'll give us x squared equals x plus 1. This is a quadratic equation. We can solve it by setting it equal to 0 and then using the quadratic formula. When we do, we end up with 1 plus or minus the square root of 5 over 2. This is actually two answers. If we use the plus sign, we get approximately 1.618. This is the answer we were looking for in the first place, the limit of the ratio of two consecutive Fibonacci numbers. This number is so famous, it actually has its own symbol, the Greek letter phi. Some people say phi. I like to say phi, but it's never okay to say pho or fum. This is commonly referred to as the golden ratio. The golden ratio has been studied by mathematicians since ancient civilization, and it's been used in countless works of art and architecture throughout history. It also appears throughout nature, especially in the spiral patterns of leaves and other parts of vegetation. So phi is about 1.618. There's also a second solution that we get when we use the minus sign. It comes out to negative 0.618. We also get the same number when we subtract phi from 1. So both of these solutions can be written in terms of the golden ratio. Let's take another look at this quadratic equation. If we add the x and the 1 back to the right side, and then multiply every term by x, we get x cubed equals x squared plus x. We already know that x squared is equal to x plus 1, so let's replace it with that. Combining like terms, we get 2x plus 1. Let's do that again with this equation. Multiply every term by x, and again, replace the x squared with x plus 1. Distribute and combine like terms to get 3x plus 2. One more time. Multiply by x, and simplify to get 5x plus 3. Do you see the pattern yet? Look at all the coefficients on the right side. These are the Fibonacci numbers. For the top equation, 1 and 1 are the first two Fibonacci numbers, f1 and f2. The next equation, 1 and 2 are the second and third Fibonacci numbers, f2 and f3. 2 and 3 are the third and fourth terms, and 3 and 5 are the fourth and fifth terms. We really have enough information now to generalize this pattern, to predict what the next equation would look like. We already know the two possible values for x, phi and 1 minus phi. So let's make two of these equations, and in the first one, we can plug in phi for x. In the other one, we can plug in 1 minus phi. Now let's subtract one of these equations from the other one. On the left side, we get phi to the n minus 1 minus phi to the n. On the other side, we have fn times phi minus fn times 1 minus phi. And since the last terms are identical, they simply cancel out when we subtract. Now let's simplify. On the right side, if we factor out the fn and distribute the negative, we can combine like terms to get this. Remember that phi is the golden ratio, which is equal to 1 plus the square root of 5 over 2. If we multiply both sides by 2 and subtract 1, we get a substitution for 2 phi minus 1, which is the square root of 5. Finally, solve for fn by dividing by the square root of 5. And we now have a formula to find the nth Fibonacci number. With phi being such an irrational number like this, the formula can get pretty messy. I recommend using a calculator. We can find the 100th Fibonacci number by plugging in 100 for n. This comes out to exactly
354 quintillion, 224 quadrillion, 848 trillion, 179 billion, 261 million, 915,075.
If you're a honeybee, that's a lot of Christmas cards to send out every year. Thank you all for watching. Be sure to like and subscribe, and have a pleasant day. Shh.